Everyone, and welcome back to the fourth question about magnetic circuit. So in this question, we have 1, 2, 3 parallel legs, and in the middle we have number of turns, which is equal to 1000, and the current that is responsible to produce the flux in this magnetic circuit is not known to us. I is unknown to us, and that is what we want to find. We will find this current. We know that relative permeability 3000 for the magnetic material. We know the cross-sectional area is 1 centimeter square, and we know the flux density A, BA, which is the flux density in the air gap A. So we know what is the flux density to the right branch. Okay, so again, the first thing we need to do, we need to draw the equivalent circuit of this magnetic circuit so that we can work with the electrical equivalent circuit. So in the middle, we have an MMF. This is your MMF, okay? And then from here to here, this mean path will result in one reluctance. I will call it reluctance 0. And then we will have two parallel branches, one to the right and one to the left. So the one to the right, we have this mean path minus the air gap, and we have the air gap. So we'll have two reluctances. One, I will call it reluctance 2, and the other one, I will call it RA. The same thing, the same name given in the question. To the left, we will have again reluctance 1, and we have reluctance of the air gap B. So this is our equivalent circuit. Okay, we will have here a flux phi, then to the right we'll have phi 1, and we have phi 2. So what we want to find, we want to find I. Okay, in other words, we want to find actually NI, which is the MMF of this circuit. That's what we want to find. Because N is known to us, once we know the MMF, then we can find our current. Now here, this flux is not known to us, okay? And all the fluxes are not known except phi 1. Phi 1 I can find because I know the flux density in the air gap A. So we know BA is equal to 1.7 Weber per meter square, or 1.7 Tesla. So from this, I can find phi 1, which is basically BA times the cross-sectional area A, which is the same everywhere. Okay, so your phi 1 will equal to 1.7 times the area is 1 centimeter square. We have to convert that to meter square. So 1 times 10 to minus 4. So this will give me 1.7 times 10 to minus 4 Weber. So now I know phi 1. Okay, perfect. I need to find phi so that I can apply KVL here to this, to the loop in the right side. But I know to find all the reluctances to do that. And back, what is the reluctance? Is equal to L divided by mu 0, mu R times A. That is the reluctance in any air gap or any path in the magnetic circuit. So let's find the reluctance one by one. Let's start with the reluctance of R0, R2, and R1, and then we will find the reluctance of the air gap A and air gap B. So we'll start with the reluctance 0, which is in the middle. Okay, so here in the middle, the length is given to us specifically from here to here. I don't need to do any calculations to find L. So this will give me 0.21 divided by mu 0 is constant, 4 pi times 10 to minus 7. Mu R is given to us as 3000. And finally, the cross-sectional area A is uniform for the whole magnetic circuit, which is equal to 10 to the minus 4, 1 centimeter square. So we do the calculations for this. This will give me 557 and 042.3 ampere turn per Weber. Okay, so I found R0. Now I need to find the reluctance R, reluctance 1 and reluctance reluctance 2. So reluctance 1 is equal to L1 divided by mu 0 mu R times A. So of course this and this will be identical. The only thing I need to find is L1. Okay, now how to find L1? L1 is the distance from here all the way until we reach here. Okay, so we have to subtract the air gap, but we need to go through the whole path. Okay, so what I know the distance between the far two ends is 33 centimeters. Also, I know another information. From here to here, it is 22 centimeters, and from the middle to the middle is 21 centimeters. It means that from here to here is 0.5 centimeter, and from here to here is another 0.5 centimeter. Okay, so basically the distance, this is 22 centimeter, this is 21 centimeter. So I can know the width. The width here, this width is basically what? 1 centimeter. So we have here 1 centimeter, here is another 1 centimeter, and here is another 1 centimeter. Perfect. So now I can find this distance. Let me call it D and D. Now it's a valid assumption now if no dimensions are given to assume that these D's are exactly the same. So basically we will have D plus D, which is 2D, plus 1, 2, 3, 3 centimeter, is equal to the overall length, which is 33 centimeter. So from this, your 2D is equal to 30 centimeter. So your D is equal to 15 centimeter. Now D is the distance from here to here. Now if I want to find the mean path from this point to this point, I need to add 0.5 centimeter to the right, 0.5 centimeter to the left. So this will be 16 centimeter. And this distance will be another 16 centimeters. And the vertical distance, which is similar to the middle branch, is 21 centimeters. So your total L1 will equal to, okay, will equal to this from here to here, which we agreed now it is equal to 16 centimeter, plus another 16 centimeter, plus the vertical length, which we already calculated as 21 centimeter, minus 0.1 centimeter. So this is equal to 32 plus 21, which is equal to 53, minus 0.1 is equal to 52.9 centimeter, or 0.529 meters. So your reluctance 1 is equal to 0.529 meter divided by the same values that we have in the middle branch, which is equal to mu 0 mu r. This is constant, doesn't change. It's the same as this value. So if you do the calculations, that you will find reluctance 1 is equal to 1403216, 1,403,216.1 ampere turn per Weber. Okay, so this is reluctance 1. We know reluctance 0. We need to find reluctance 2. Reluctance 2 is this. Now you can see here clearly that reluctance 2 is equal to reluctance 1 minus just 0.1 centimeter. Why? Because the air gap here is 0.2 centimeter or 2 millimeter, and here is 1 millimeter. The rest is exactly the same. So your reluctance 2 is equal to 0.528 meter. Of course, divided by, this is actually not reluctance 2, this is actually L2 is equal to L1. Okay, so now if you want to find reluctance 2 is equal to 0.528 divided by 4 pi times 10 to minus 7 times 3000, which is your mu, times area 1 times 10 to minus 4, and this will give me 1,400,563.5 ampere turn per Weber. So now we found reluctance 1, 2, and 3. Now we need to find reluctance of the gap A, which is the distance, which is 2 times 10 to minus 3 divided by mu 0 only, because this is an air gap, 4 pi times 10 to minus 7 times the cross-section area, which is 1 times 10 to minus 4. And this is equal to, your RA is equal to total value of it, 1,591,549.4.3. So this is your RA ampere turn per Weber. Your reluctance P is equal to exactly the same thing, but this is would be 1 times 10 to minus, so it's half over 3 minus 3, 4 pi times 10 to minus 7 times 1 times 10 to minus 4, and this will give me 7,957,747.2 ampere turn per Weber. Now let's draw again the circuit, okay? And let's do it here, okay? So this is my circuit. We will have reluctance 0. We have my MMF, and I will have reluctance 2, and here we have reluctance A. Now we have reluctance 1 and reluctance B. So all the values we already know. We know reluctance 0, reluctance 1, we know reluctance 2, we know reluctance A, and we know reluctance B. So all the reluctances are given to us, plus we know the flux phi 1. We know this flux phi 1. Okay, now we want to find this flux phi so that we can find the MMF. Now we will apply current dividing rule. So this flux phi 1 actually is equal to the main flux phi times the reluctance of the other branch, which is reluctance B plus reluctance 1, divided by the summation of these two reluctances in parallel, which is RB plus R1. So this is the left branch plus RA plus R2. So everything is known to us. All the reluctances are known, and phi is the unknown, and reluctance 1 is known to us. So we want to find actually phi, which will be equal to phi 1 times the summation of all reluctances RB plus R1 plus RA plus R2. This is divided by R1 plus RB. So this is my unknown. This is, I know it, 1.7 times 10 to minus 4. Now, when we substitute with all these values, you will find that the main flux phi is equal to 4.84 Weber times 10 to minus 4. So this is my main flux. Okay. Now, I know this flux, I know this flux, I will apply KVL to this. And of course, we use the passive convention. So this is plus minus, plus minus, plus minus. Okay. So your MMF equal to Ni is equal to phi 1 times reluctance 2 plus reluctance A, which is the MMF of this branch, plus phi times reluctance 0. And from this, you can find your I is equal to phi reluctance 2 plus reluctance A plus phi reluctance 0 divided by N. Everything is known to us. So from this, you can find your I, which is equal to 3.21. So you can see this question here from the beginning. We know the flux density here. We need to find the flux here, phi 1. Then we need to find all reluctances. And then we need to find the original flux. And from that, we can apply KVL to this loop so that we will find the MMF. And from that, you will find your current as MMF is equal to N times I.